Hey, this is Presh Talwalkar.
Today, MIT is one of the top universities in the world. In 1876, their entrance exam contained a section on arithmetic. One part of a question caught my attention, which was to extract the square root of 11.56. How are you supposed to do that without a calculator? There's a similar question in the entrance exam of Harvard University in 1869. One part of a question asked to find the square root of 531.5 to 3 places of decimals. Now I was definitely curious. What was the method students had learned to figure out the square root of a number digit by digit? And why had I never learned this in school through my math degree at a university in America? While researching these questions, I did find an answer to the second part. I never learned this in school or any books because educators think it should not be taught to students. To give a reason why, let me go through some math history in America. There was a time when people learned the square root method. Here's a text from 1966 from the Bureau of Naval Personnel describing the square root process. It explains how to calculate square roots, and it gives an example of calculating the square root of 9,025. They provide a calculation and show the answer is 95. But something happened in America in the 1960s called New Math, where instead of focusing on the traditional techniques and calculations, they decided to talk about things like set theory, understanding, and different number systems. As a consequence, they had a different focus. When they were talking about multiplication and division, for example, they were talking why learning the algorithm for long division is not a good idea. So if you've ever tried to calculate division and you've learned a method where you do long division like this, they're saying this was something that was very bad. They didn't want this taught in school. Learning one or more algorithms for long division is exactly the kind of task that accentuates and intensifies the worst aspects of schools today. We have here a topic which teachers are unsure of, which many teachers dislike, and which they feel their students must master because of its prominent role on tests. It is a topic which has been taught traditionally by rote, and it is not easy to teach in an exciting or meaningful way. Thus, it is a natural point of concentration for the negative aspects of school. It is unpleasant. Teachers will tend to bear down hard on students. The conversation will be mainly in terms of meaningless rote, and teachers will demand conformity. As such, it may be one of the major contributors to the early disaffection of youngsters, not only with mathematics, but with school. Much the same was true of the old algorithm for finding square roots, but with two important differences. The square root algorithm was not considered especially important, and it did not occupy much school time. The resolution of the problem in the case of the square root algorithm has been mainly to delete it and to replace it by the far more insightful method of guess, divide, and average. So if you believe these educators, we shouldn't be teaching long division algorithms in school, and we definitely shouldn't teach square root algorithms, because not only will it make students not like math, but they will also dislike school in general. So this is your fair warning. You can stop the video right now if you don't want to learn this method. But for the rest of us who are throwing caution to the wind, let me explain the digit by digit method for calculating square roots. In this video, I will describe a way you can calculate the square root of any number digit by hand, and you can calculate it to any degree of decimal accuracy. Let me begin with an example of computing the square root of 2025. The first step is to prepare the number. Start with the first digit that's closest to the decimal point. From there, mark off pairs of digits. So we will mark off 5 and 2 as one pair, and 0 and 2 as another pair. The number of pairs will tell us the number of digits in the integral part of the square root. So we already know that the integral part of the square root will have 2 digits. So let's just rewrite this number in terms of pairs. We will now start from the left, and the process will be much like the long division algorithm. So we first have the number 20. We want to compute a divisor, and the divisor will be the square that's closest to 20 but not exceeding 20. So 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, but then 5 squared is 25, and 25 is larger than 20. So we want the largest square that does not exceed 20, and that will exactly be 4 squared, which equals 16. So we start with a divisor of 4, and we have a partial quotient of 4. 4 times 4 is equal to 16. Take this product and subtract it from 20. The result is 4. We now pull down the next pair of numbers. So we will pull down 2 and 5 so that we have a new number, 425. Now we need to create another divisor, but it's going to be a little bit complicated. This is the only difficult part of the process. So what you do is you take your previous result, so whatever the previous quotient was, which is 4 in this case, and you are going to double it. So 4 times 2 is equal to 8. We now need to modify this divisor. So let's say the next digit is b. We are going to append b so that we have the number 8b, or 80 plus b. We now need to take 8b times b and not exceed 425. In other words, we need to calculate b that solves 8b times b is less than or equal to 425. Now let's use some estimation skills. So if we have 80 times 1, that's 80, but 80 times 10 will be 800. 425 is right in the middle of that, and it also ends in a 5, so a natural candidate for b will be b is equal to 5. So let us try b is equal to 5. So if we substitute b is equal to 5, let's do this multiplication. 5 times 5 is equal to 25, so we put 5 down and carry over the 2. 5 times 8 is equal to 40. 40 plus 2 is equal to 42. And 85 times 5 is exactly 425. So b equals 5 perfectly works. So we're going to substitute b is equal to 5. We have a product of 425. And when we subtract that from 425, the result is 0. So we have no remainder at this step, and the process concludes. We have figured out the square root of 2025 is exactly equal to 45. And you can in fact check that 45 squared is equal to 2025. Now let's continue with another example of calculating the square root of 831,744. Starting with the digit closest to the decimal point, we will mark off pairs of digits. So we will mark off 4 and 4, then 7 and 1, and finally 3 and 8. So we have 3 different pairs, which means the integral part of this square root will have 3 different digits. Let's just group these pairs. Like long division, we start out from the very left, so we take a look at 83. Now, what square is closest to 83 but does not exceed 83? We will go all the way to 9 squared, which equals 81. So we have a divisor of 9, a quotient of 9, and 9 times 9 is equal to 81. Subtract that from 83, and we get a result of 2. We will now bring down the next 2 numbers of 17. We now need to figure out the next divisor. So we take the result of 9, and we are going to double it. 9 times 2 is equal to 18. Suppose the next digit is b. The next divisor will be 18b, or 180 plus b. So we need to solve 18b times b does not exceed 217. But this is relatively simple to do, because if we just try b is equal to 1, we're already at 181, and if we go to b is equal to 2, we will exceed 217. So it's clear that b is equal to 1. Now we put down the next product, and we subtract 181 from 217. Let's do this by counting up. If we add 19 to 181, we get to 200, and then we just add 17 to get to 217. So we add 19 and 17, and the result will be 36. We now bring down the next 2 digits of 44. What will the next divisor be? We take the result from before, which is 91, and we are going to double it. So 91 times 2 is 182. Suppose the next digit is c, the divisor will then be 182c. So we need to solve the equation. 182c times c is less than or equal to 3,644. But this is easy. If we substitute c is equal to 2, we get exactly 3,644. So we know that c is equal to 2, we get 3,644, and we end up with no remainder, so the process ends right here. So we know the square root of 831,744 is 912. And in fact, we can check that the square of 912 is exactly 831,744. Let's proceed to another example of the square root of 13,689. Starting from the digit closest to the decimal point, let's mark off pairs of digits. So we have 9 and 8, then we have 6 and 3, but now we only have one digit here. But that's okay, we will keep this as its own group. So we will mark off this number as 3 different groups, so the integral part of the square root will be 3 digits. So let's separate these groups. We now start with the number on the left, which is 1. So what number doesn't exceed 1? Well, of course, that's going to be 1 squared. So we know we have a divisor of 1 and a quotient of 1, and 1 times 1 is equal to 1. So we subtract that from 1 and we get 0. Now we bring down the next two numbers, which is 36. Now we take the result of 1 and we multiply it by 2 to get the next trial divisor of 2. If the next digit is b, we know that the divisor is going to be 2b. So we need to solve 2b times b is less than or equal to 36. Well, in this case, b is going to have to be equal to 1 because 21 times 1 is already 21, and if we go one more, we would exceed 36. So b is equal to 1. Then we have 1 times 21 is 21. We subtract that from 36 to get 15, and we bring down the last two digits of 89. We finally take 11 and we multiply it by 2 to get the next trial divisor starts out with 2, 2. If the next digit is c, then the divisor is going to be 2, 2c. So we need 2, 2c times c is less than or equal to 1589. Now we're going to do some estimation. 220 times 6 is equal to 1320, and 220 times 7 is 1540. So it seems like 7 is going to be the number that works. And if we substitute c is equal to 7, we get that 227 times 7 is exactly equal to 1589. Therefore, we have c is equal to 7, the final product is 1589, and we end up with no remainder. So we have extracted the perfect square root. So we have the square root of 13,689 is 117, and in fact, the square of 117 is 13,689. Let's now level up to the next example of the MIT entrance exam from 1876. Find the square root of 11.56. Now, when we prepare the number, we have to prepare the decimal part a little bit different. So we start out with the decimal point, and we look at the digits to the left of the decimal point when we're pairing to the left of the decimal point. So we're going to pair from the decimal point 1 and then 1. When we go to fractional parts of the number, we're going to start from the decimal point, so we're going to pair 5 and 6. So we have two different pairs, 11 and 56. So as usual, we start out by analyzing the first pair, which is 11. So what square does not exceed 11? That will exactly be 3 squared, which is equal to 9. 11 minus 9 is equal to 2. We now have a decimal point, so that's going to appear in the answer at this point. But for the rest of the calculation, we can just kind of ignore this decimal point. So we're going to bring down the next two numbers of 5 and 6. We now need to get the next divisor. So we take the result of 3 and we multiply it by 2 to get 6. Suppose the next digit is b, we will then have a divisor of 6b. So we need 6b times b is less than or equal to 256. Well, this should be known to everyone in computer science. Of course, 64 times 4 is equal to 256, so we know that b is equal to 4. So we take b is equal to 4, and we figured out that the next product will be 256. We subtract that and we have no remainder. So the square root of 11.56 is 3.4. And in fact, the square of 3.4 is equal to 11.56. Congratulations, you could have gotten into MIT in the year 1876. Let's now level up to the next example of the square root of 1,234. This number is not a perfect square, so we're going to need to approximate it to some level of decimal accuracy. So let's say we want exactly 2 decimal digits. So here we have a decimal point, and let's extend the square root. So if we want 1 digit after the decimal point, we will need 2 zeros for that. If we want another digit, we will need another 2 zeros. So the number that we want to analyze is 1,234.0000. Now let's divide this number up into pairs as we've been doing. As usual, we start from the left, and the number we analyze is 12. What square is closest to 12 without exceeding it? That would be 3 times 3, which equals 9. We then do 9 minus 12, which is equal to 3. We bring down the next 2 digits of 3 and 4. To get the next divisor, we take the result of 3 and we double it to get 6. If the next digit is b, the number we're looking for is 6b. So we want 6b times b to not exceed 334. Let's do some estimation. If b is equal to 4, 64 times 4 is 256. If b is equal to 5, we can break up 65 as 60 plus 5 and use the distributive property. So 65 times 5 is equal to 60 times 5 plus 5 times 5. 60 times 5 is 300, 5 times 5 is 25, and this is equal to 325. So clearly b is equal to 5. So we will take the value of b is equal to 5 and put the next product of 325. We subtract that from 334 to get 9. Now we have a decimal point, which we will just put as part of the answer, but we will just ignore it and bring down the next 2 numbers of 0, 0. We now need our next trial divisor, so we take the result of 35 and double it. 35 times 2 is equal to 70. Suppose the next digit is c. The number we want is 70c. So we need 70c times c to not exceed 900, and clearly we will need c is equal to 1. So this is an easy calculation because 701 times 1 is equal to 701. Anything higher will exceed 900. So we bring down 701 and subtract that from 900 to get 199. We bring down the last 2 zeros. Now we take 351, we're just going to ignore the decimal point, and we're going to double that, which will be 702. Suppose the next digit is d, then we have 702d multiplied by d has to be less than or equal to 19,900. And in this case, d is equal to 2 is the value that's going to work. So if we take d is equal to 2, we have the product here. And notice we're going to end up with a remainder that's not 0 because we could continue this process. We don't have an exact answer. But we have figured out the 2 decimal digits that we want. So the square root of 1,234 is approximately equal to 35.12. We have found 2 correct digits after the decimal point. Notice the next digit would actually be 8. So this would actually round up to 0.13. So we are not getting 2 digits of accuracy. If you need 2 digits of accuracy, you have to compute out to 3 digits so that you can know which way we're rounding. But in this example, we just wanted to get 2 correct digits after the decimal point. So finally, let us now tackle the Harvard University question to find the square root of 531.5 to 3 places of decimals. In this video, I will present how to calculate 3 digits after the decimal point. These will be 3 correct digits, but if you need 3 correct digits of accuracy for rounding, you will actually need to calculate to 4 digits. So in order to get each digit, we will need a pair of double zeros. So we will need 0, 0 for one digit, 0, 0 for another digit, and 0, 0 for the third digit. So we will need to calculate out to 6 places after the decimal point. Now 531.5 already has 5 in the first spot, so we're going to need to add 5 zeros. And we're going to parse the number as follows. Notice that we have 1, 3 as a pair, and we have 5 as a standalone. And then we have 5, 0, 0, 0, and 0, 0 as different pairs. So let us take the square root of 531.5 to 3 digits after the decimal point. So we start with the 5, and we need the largest square that does not exceed 5, which will clearly be 2 squared, which is equal to 4. We then have 5 minus 4, which is equal to 1. Carry down the next 2 digits, which is 31. To get the next divisor, we take 2 and we double it to get 4. Suppose the next digit is b. We then need 4b times b to not exceed 131. And after doing some calculations, we get that 43 times 3 is equal to 129. So the next digit will be 3. We then have the result of 129, which we subtract from 131 to get 2. We have a decimal point here, which we're just going to ignore when we carry down the next 2 digits, but it will affect the answer. So we have 23 point something. We now double 23 to get the next divisor of 46 something. So if the next digit is c, we have 46c times c must not exceed 250. 461 times 1 is already larger than 250. So in this case, we know the digit has to be equal to 0. So we just have 0 as the product, and we have 250. We then carry down the next pair of zeros, so we have 25,000. We then take 230 and double it to get 460. If the next digit is d, we have 460d times d must not exceed 25,000. Omitting the laborious grunt work, you will eventually get that the digit has to be equal to 5 because 4,605 times 5 is equal to 23,025. So d is equal to 5, and we have the next product. Subtract that from the previous result to get 1975. Finally, bring down the last pair of zeros. So we take the previous result, 2305, and double it to get 4610. If the final digit is e, we need 4610e times e to not exceed 197500. After doing quite a bit of calculation, we will get that e has to be equal to 4. And this is the next product. So clearly, there is some difficulty in this algorithm. It does get more and more difficult as you want more and more digits. But this is a good way to really practice your times tables and estimation skills. So we put down the final digit of 4, and we put the last product, and we can see that the remainder is not equal to 0. We haven't exactly figured out this square root, but that's okay. For the purposes of this question, all we wanted to do was calculate 3 correct digits after the decimal point. So we get that the square root of 531.5 is approximately equal to 23.054. And congratulations, you could have gotten into Harvard in the year 1869. I will conclude the video with a bit of history, a justification of why this method works, and a little bit of perspective on understanding the square root algorithm and why it's important. So let's start out with who invented this algorithm. It actually dates back to the great mathematician Aryabhata in the year 500, who actually put this algorithm down as a poetic verse in Sanskrit. It would be like a combination of doing mathematics and Shakespeare at the same time. For those of us who don't read Sanskrit, there's a blog that translated the algorithm. It says to divide the even places by twice the square root of the result made so far. From the odd places, reduce the square and add that digit which was squared to the result. And that's exactly the algorithm that's produced in this video. I should mention, this is one method to calculate the square root of a number digit by digit. But it's not necessarily the most efficient. It does get more complicated as you try to extract more and more digits. And in fact, it's not the only known algorithm since ancient times. There were other square root methods that did exist. For another algorithm, I refer you to a different video I made, which was an ancient trick that the Babylonians had to calculate any square root to any level of accuracy. they would basically come up with a guess for the square root, then look at the difference from the value, and then use that as the new guess and iterate this process. It was actually a geometrical derivation, which was definitely wonderful. So do check out that video. This is more similar to how calculators and computers actually do calculate square roots. But why exactly does the digit by digit method work? Let me give you a justification by doing an example of the square root of 2025. So we have two different pairs here. So we know that the integral part will have two different digits, a and b. But the number ab is equal to 10a plus b because a is in the tens place. So let's set up the equation. The square of 10a plus b is equal to 2025. If we expand this binomial, we get 100a squared plus 20ab plus b squared. From these two terms, factor the variable b. So we have b times 20a plus b. We will then split up 20a as 2 times 10a. So let's see how this equation relates to the process. We first take a look at 20, and we need the largest square that doesn't exceed 20. So we're going to figure out that a is equal to 4. So what we really have is 4 times 4, which is 16, multiplied by 100. That will be 1600. Now, in our calculation, it's always going to have two zeros here, so we're just going to omit those double zeros. So we have 1600 already accounted for by this 4, and when we subtract that from 2025, we end up with 425. We now need b to make up the rest of 425. But what is remaining once we have 100a squared? Well, we have 2 times 10a. And this is why we double the previous result. So this is 10a, and we are going to double that to get 8. What do we do from there? If the next digit is b, we are adding b. So here we have 80b, which is 8b. We need to multiply this number by b, and that's why we set up the problem 8b times b should not exceed 425. What value of b works here? Well, exactly b is equal to 5 is the value that works, and 85 times 5 gives us 425, and we end up with no remainder. So we've exactly extracted the square root of 2025, and it relates to this equation. Now let me show you a geometrical derivation as well. So let's say we have a square, and we need its area to be 2025 square meters. So let's say we get the first number, which is 40. So we have a square that's 40 by 40, and that takes up an area of 1600 square meters. Now, how do we get the remaining area? It'll be 425, and it will be divided up into 3 different rectangles. So let's say the remaining length is equal to b. One rectangle will have an area that's equal to 40b, as will this rectangle, and the remaining rectangle will be a square, which has an area of b squared. So the amount that remains is 80b plus b squared. We can factor a b to get b times 80 plus b. So notice if the next digit is b, we have to double this 4 to get 80 plus b, and this is another explanation of why we have 80 plus b times b, and of course b will be equal to 5, and this exactly accounts for the remaining area. So this is a geometric way to see why this algorithm works. I will conclude the video with a perspective on the importance of the place value system. Until about the 1500s, much of Europe was using Roman numerals. So calculating the square root would have been written as a problem like the square root of mmxxv for 2025. How would they perform this calculation? They would actually use the aid of an abacus. They would convert this number in Roman numerals to a position on the abacus. They would then perform some procedure on the abacus. And finally, they would convert that result on the abacus back into a number. There were many flaws with this procedure. First of all, you're transcribing numbers back and forth. And secondly, there's no way to actually verify what someone does on the abacus. You can't check someone's work. So it was actually computationally very annoying. Now, if instead you state the problem with the current numeral system we use, the base 10 positional system, it is truly a remarkable accomplishment that you could perform the arithmetic right on the numbers, and you could show the result and people could check your work. Clearly, the square root of 2025 is equal to 45, or 45 squared is equal to 2025. But not all revolutions are accepted by society right away. There was actually a strong feud in Europe between the people who used the base 10 number system and the calculations along with it. They were known as algorists, and the other group of people who used Roman numerals and said it was better to use an abacus, and they were known as the abacists. These two groups actually would have competitions about calculating things faster, and it was portrayed in this work of art that which system of arithmetic is actually going to work out. And you know which system won out because that's the system we're taught in school. But this great accomplishment is not often given the credit it deserves. The great mathematician Laplace lamented in the year 1795, "It is India that gave us the ingenious method of expressing all numbers by the means of 10 symbols, each symbol receiving a value of position as well as an absolute value." A profound and important idea which appears so simple to us now that we ignore its true merit. But the very simplicity, the great ease which it has lent to all computation, puts our arithmetic in the first rank of useful inventions. Thanks for making us one of the best communities on YouTube. See you next episode of Mind Your Decisions, where we solve the world's problems, one video at a time.